Good morning everyone. So we are going to present a video presentation for MAT183 and the topic is application of differentiation, chapter 3, which is apply maximum and minimum. So before we start, I'm going to introduce our team members. My name is Leslie Leo Anna Buckner and my second member is Wen Rooney Gabriel, and also the last one is Alia Sufina binti Hisham Hafiz. Now I'm going to present the introduction for our video presentations. So, what is related rates? Related rates is a method that we use for calculus to find rates which quantities change with respect to time that related with each other. This application of differentiation focus more on relationship between variables and also derivative. So, what is the reason that we should use related rates? Related rates can help us to handle the interconnected change, which is mostly in a real-world situation where the variables are dependent on each other.
So our question is about an eco-friendly box, a packaging company specializing in sustainable design. They took on the challenge of creating a new open-top box for shipping glass items. The goal was to maximize the box storage capacity while minimizing material waste, all from a single sheet of cardboard. The team started with a rectangular piece of cardboard measuring 12 cm in width and 48 cm in length. To form the box, they planned to cut equal-sized squares from each corner and fold up the sides. Their objective to design the box in a way that achieved the largest possible volume. So next, we go to the solution step. So first, which is labeling, we have X as width, L as length, V as volume, and H as height. So for the second step, we need to determine which is it maximum or minimum. So for our question, we need to find the maximum volume. The third step, we need to find the volume formula, which is for rectangular, we need to multiply L and multiply W and multiply H, which is the width, the length, and the height. So for the first step, which is differentiate V with respect to X, where we differentiate the Vx, then we got 576 minus 240x plus 12 square. Okay, so next we'll be looking at the fifth step, which is finding the x. So first, we need dx over dv over dx becoming 0. Then we need to simplify the equation. Then we put it into a quadratic equation. Then we got x equals to 17.211 or x 2.789. Okay, so we choose x equals to 2789 is because x 17.211 becomes negative when we substitute it to the length equation. So x equals to 2789 is the only valid solution. So next we'll be looking at the sixth step, which is prove volume is maximum. So here we need to prove whether it is maximum or minimum. So here the answer is negative, meaning it is maximum. So for the last step, it is maximum volume. So it is where we substitute the value of x into our V equation. So the total is 789.819 centimeter cube.
In conclusion, through the use of mathematical optimization and calculus, the maximum volume of the open-top box was accurately calculated. By applying the derivative of the volume function with respect to the side length of the squares to be removed, we found that the ideal side length of the squares is 2.789 cm. This corresponds to the critical point where the volume function reaches its maximum, resulting in a maximum volume of approximately 759.819 centimeter cubed. The second derivative test confirmed that this critical point is indeed a maximum. This ensures efficient material usage while maximizing capacity.